Hello everyone. The MIT Integration Bee 2023 was just held a couple of weeks ago. For the qualifying round, contestants are given 20 minutes to work through 20 integrals, which sounds like a really short period of time. Thankfully, contestants are only required to write the answer and not required to show the detailed workings. In this video, we will be going through the first 10 problems, and what we'll do is we'll also go through the more detailed working and motivating ideas behind them. So without further ado, let us take a look at what interesting integrals are in stock for us. So for the first problem, we have a rather quirky looking integral over here, but this is actually a pretty nice warm-up problem, because typically for such integrals like this, the common trick is to use the well-known expression a equals to e to the ln a. So this is actually a common trick used for such integrals, and you'll see why once we start deploying this trick. So let's deploy this trick and see what happens. So what we have here is we write this as e to the ln of the original expression. So over here we have this expression over here, and with the use of such trick, the typical thing that happens is that the expression in the power cannot be brought down in front of the ln, and usually this results in a simpler expression. And in this case, we see that if we bring down the power, we indeed have this new expression here, and ln x cancels out the 1 over ln x here. So this is really just integral of e dx. So this is just ex plus c. So a very quick warm-up for problem 1. Just a simple observation, nifty little trick, and you're on your way to start. So let's take a look at problem 2. Okay, for problem 2, we have the hyperbolic secant over here, and for some people, you might know what is the answer immediately, but actually there's no need to have seen the integral before. What is most critical for this problem is to know the definition. So the definition of hyperbolic secant is 1 over hyperbolic cosine, right? So in this case, cosine, hyperbolic cosine, you flip that, you get 2 over e to the x plus e to the minus x over here for your integrand. Okay, now having e to the x and e to the minus x in the denominator is pretty annoying. So one natural thing to do is you multiply top and bottom by e to the x. So this is so that you have only one copy of x term in the denominator. So you have this expression over here now. At this stage, you might recall that, okay, so now we have like something that looks like a square plus 1. So this should recall the integral, that if we have integral 1 over x squared plus 1 dx, then this is actually the arctan of x. And I mean similarly, if we have the integral of f prime x over fx squared plus 1 dx, then this is the arctan of fx. This is simply from the chain rule. If you had differentiated this, then you will get the original expression of 1 over f squared plus 1, but then you also have the differentiated version of f appearing here. So let me just put in the plus c for good practice. Okay, so in this case, you see that we have the exact form here that is given by this formula here. So this gives you, this is just 2 of arctan of e to the x plus c. Yeah, so this comes down again to a nifty little observation. So you start to realize that actually for the first 10 problems of this year's qualifying round, a lot of them comes down to having a single observation, and there isn't a lot of very tedious algebraic manipulation or tricky trigo substitution. So let's take a look at problem 3 and see if this continues. So for problem 3, it looks fairly complicated, but what you will notice is you have the 1 plus e to the x here in the log, and you have another 1 plus e to the x here. So it looks like one thing you might want to try is differentiate this log expression here, because when you differentiate the log of f, the f appears in the denominator. So why not let's put some ideas in the parking lot. What happens if we differentiate log 1 plus e to the x? Indeed you get this is e to the x over 1 plus e to the x. And this expression over here matches up very nicely with this, right? And what we have just differentiated is precisely the remaining part of the integrand. So very quickly you realize that this is simply the log of 1 plus e to the x plus c. Again, to recap, if you had differentiated this, firstly you need to differentiate the inner term, which is what you will get the circled term, and then you will need to divide by the original expression, which is where I'm pointing my arrow now. So this is a one-line solution that relies on making a very sharp observation, which I think is what makes a good integration problem. So let's see if this holds for problem 4, which might look a bit tedious. So we have a rather scary looking polynomial times polynomial thing here. Now you might think, on the one hand, this looks easy because the integration of polynomial is the easiest type of integration problem. But on the other hand, you might think that if I had to expand this, I have to it's a 25 term expansion, so it might be a bit tedious. But thankfully, if you had decided to bite the bullet and go ahead with the expansion, you can do the expansion in a very quick way. So if we have a table to keep track of what are the different terms that are in the expanded form, you realize that if we take the first term 1 and we multiply, we distribute it out across the various terms in the second bracket, then you will have coefficients 1, minus 1, 1, minus 1, 1 being contributed here. And then now if we take the second term x and we expand out across the second bracket, then you will realize that again you have 1, minus 1, 1, minus 1, 1, except now the terms are displaced by 1. You have the lowest power is x. So the expression is quite simple. You basically have 1 minus 1, 1 minus 1, 1, but each time you displace your power of x by 1. So you have this 5 times. And then now you can very easily find the sum, because this minus 1 and 1 cancels, this cancel, all this cancels out each other. So what you are eventually left with is very simply just 1 plus x squared plus x4 plus x6 plus x8. So in other words, if you had decided to expand this in the exam, of course, you can just mentally note this, and then you will very quickly reduce the problem to this integral. So this integral is x plus 1/3 x cubed plus 1/5 x5 plus 1/7 x7 plus 1/9 x9 plus c. So that is really all to this problem. And let us take a look at problem 5, which looks really interesting. In the first place, what exactly is the x choose 5 function? So let us first note that by definition, x choose 5 is given by what you will expect. So x minus 1, x minus 2, x minus 3, x minus 4 divided by 5 factorial. Now, you will notice that the integral is intentionally chosen to be a definite integral from 0 to 4. So you will stare hard at this expression, and if we call this f of x, what you might notice is that f of a number a is equals to minus f of 4 minus a, meaning your function, I don't know how the function looks, I'm just going to draw something that is really weird looking. Okay, this is not a good idea because there are so many things wrong with that, but basically your function from 0 to 4, if you have some value here at a, the value at 4 minus a is the negative of it. So in some sense, this is like an odd function around x equals 2. So if you have integral from 0 to 4 of f, where f is basically like negative symmetric around 2, then this would be equal to 0. Okay, let us take a look at problem 6. So over here, we have a trigo integral. We have x plus sine x plus x cosine x plus sine x cosine x, which looks like a very mouthful and complicated looking string of terms, but it looks very suspiciously factorizable, and indeed we can write this as x plus sine x times 1 plus cosine x. So let's quickly check. If you expand this, we have x plus sine x plus x cosine x plus sine x cosine x. So indeed, we have this factorization, and now you notice that if we take the differential of the first one, we get the second one. So this basically gives us the required answer. Once we notice this is quite straightforward, we will want sine x squared, so that you bring down the power of 2. It cancels the half here. You get the original expression times the differentiated expression. So this is the final answer. So we are back on track on the nifty observation train. So let's hope this keeps up. Wow, question 7. This is a string of trigo squared. So when you see a question like this, what you will want to recall are the square trigo identities. So obviously sine squared plus cosine squared plus 1 is the most fundamental one. And if you divide by cosine squared throughout, or rather if you divide by cosine squared throughout, what you get is tangent square plus 1 equals secant square. And then you have 1 plus cotangent square equals cosecant square. Okay, so this gives you some starting ideas. Obviously, you know how to integrate 1. But in fact, you also know how to integrate secant square and cosecant square, because the integrals are respectively tangent x and minus cotangent x. So, sorry, minus cotangent x is just this, yeah. So, you can actually use these expressions to get rid of the tan square and cotangent square into some things that we know how to integrate. So without further ado, let's try and deploy this idea. Firstly, we have a factor of 1 here. And in order to get rid of the tan square and the cot square, we will want to have a factor of 1 that pairs with each of these. So this inspires you to minus 1 add 1, so that there's no change to the integral, but you introduce another copy of 1. Then we have plus 1 from the sine square cos square. And then we have plus tan square x plus cot square x plus secant square x plus cosecant square x dx. And then now you pair this copy of 1 with tan square, pair this copy of 1 with cot square. Then you get integral minus 1 plus, now we have another copy of secant square x, and we have another copy of cosecant square x. Yeah. Aha, and so now this is just a straightforward integral. It's minus x plus tan x minus cot x. Oh, sorry, 2 tan x and 2 cot x plus c. Okay, so hopefully you enjoyed this problem too. It's pretty nice. Let's take a look at question 8, which is my favorite problem from this set. So we have the integral from 0 to 2 pi of the floor of 2023 sine x. So when you first see this integral, you might be thinking, that's impossible. Like, there's no known formulas for integrating like floor functions, right? So you must reason to yourself that therefore this is not about applying a formula, but more about reasoning numerically the idea of integral under an area. I mean, area under the curve being the integral. So let's try and take a look at how the function behaves. So if we have, let's say over x here, and over here I draw the 2023 sine x function. So we have something like this. Okay, so the height of this is 2023, but now we need to take the floor function. So let me just say this is from 0 to 2 pi, right? And now we need to take the floor function. So let's think about how the floor functions behave. If we have some piece of the curve here, and it runs from k to k plus 1, so inclusive of k but exclusive of k plus 1, then this piece of the sine curve would be, after performing the floor function, it will be converted into just k, right? So just this segment will be converted to a value of k. And let's say this segment runs from a x value of, let's say a to b, okay? Then if you recall the symmetric properties of the sine curve, if we go look at the segment from pi plus a to pi plus b, so we shift the segment by pi, what happens? So we have a corresponding green segment, right? And this green segment, what are the values? I mean, at pi plus a, sorry for the non-straight line here, but at pi plus a, the value will be negative of the value at a, right? So this will be minus k. And at pi plus b, the value will be minus k plus 1. And this time, if we take the floor function, what you'll get is this whole segment will be at minus k plus 1. So this means that if you pair this segment with this segment, the net area under the curve, so the net area under the curve is this part, right? As well as this part, which is now negative. So the net area is actually minus 1, because this is not one time, but 1 unit more negative than how positive this part is. So it's minus 1 times the length of the segment. So now what you do is you consider all segments across from 0 to pi. If you match with the corresponding segment from pi to 2 pi, the corresponding segment will always have minus 1 more negative than the earlier segment. So what this means is that the answer is just minus 1 times pi, which is minus pi. So a brilliant problem that doesn't test you on sophisticated formulas, it tests you on reasoning. So hope you enjoy this problem. This is my favorite problem from the set. But now I'll talk about another problem that comes close. So this one is a rather complicated looking integrand. We have firstly this e to the log x quantity squared. It looks like there's no standard formula for this. But then again, if we think about where this term looks familiar, it is because if we differentiate this, the exponent, when differentiated, will produce something that looks like 2 log x. So this suggests that, okay, let's not try and get ahead of ourselves, and let's first put in the parking lot one idea. If we differentiate e to the ln x square, what happens? Right, first we get 2 ln x, but we need to differentiate ln x, so get 1 over x, and then e to the ln x square. So the 2 ln x does appear. How about the plus 1? And why is there a 1 over x on this side? So not to worry, this looks like a good start. We at least have the 2 log x, right? So what you will try and do is maybe, let's not care about the plus 1 for now. So let's see, how can I evaluate just 2 log x e to the log x squared dx. Okay, but we only know how to integrate this expression when there's a 1 over x inside it. So this suggests that we multiply and divide by x. So we have, after multiplying and dividing by x, we have this expression here. And now we know how to integrate this. But at the same time, this other part is easy to differentiate. So this suggests we use integration by parts. So we have x and then times the thing that after being integrated. So this is this expression based on our result in the parking lot. And then minus differentiating x, we have 1, then times e to the ln x squared dx. And then now we realize that this copy of 1 here is the plus 1 here. So if we had moved this entire thing to the left hand side, then what we have is the integral of 2 ln x plus 1 e to the ln x squared dx is equals to x e to the ln x squared plus c. So another elegant problem. Hope you enjoyed this problem as well. I really like this problem too. And lastly, we'll look at problem 10, which looks like a ginormous algebraic expression. So since this is a polynomial, obviously if you can simplify the whole thing into a single string of polynomial, then you can directly integrate it. But of course, in the contest, you won't have time to do a direct expansion, right? So the key is to then think through what is the trick that should be used to simplify the expansion process. And what you realize is that there's a copy of 1 minus x in all the terms. So there's a copy of 1 minus x here. And then what is this? This is x times 1 minus x. And then how about this? This is minus of 1 minus x, 1 plus x. Right? So same thing, though this is the 1 minus x, this is x times 1 minus x. And then this is minus of 1 minus x, 1 plus x. Right? So this suggests that we can pull out a copy of 1 minus x cubed from each of the 4 terms here. So if we pull out a copy of 1 minus x cubed from each of 4 terms, we get 1 plus, so this one is left with x cubed, right? And then this is left with minus 1 plus x cubed. And then over here, we have, I will combine the minus sign out with the minus 3 in front. So plus 3 x times 1 plus x, right? We have the x from here and the 1 plus x from here. So this simplifies slightly. At least we pull out the copy of 1 minus x cubed. But then now you realize something. These terms that I have underlined over here, what do they sum up to? This actually sums up to 1 plus x cubed. So what a surprise. We have 1 plus x cubed minus 1 plus x cubed. And this, therefore, expression evaluates to 0. So the whole integral itself evaluates to 0. So that's all for the problems in the first half of the qualifying round. I hope you enjoyed this video. Stay tuned to the channel for the second half, which will be coming very shortly. So subscribe to the channel and see you soon.